is actually going to be. Obviously, since we're talking about computing, all of this data is going to be stored in binary format. Now, essentially, whenever you had to look at an audio signal, all right, an audio signal is essentially fluctuations of amplitude across time. In fact, sound waves in of themselves are very periodic. All right, they sort of like repeat themselves in the form of waves. All right, as we can see via this curve here. This is a simple sine wave. All right, and what we're doing when we are actually capturing audio, all right, via microphone, is that at a predetermined time interval, we are measuring, all right, the amplitude that we are capturing via the microphone. All right. Now, as we said, all right, the number of samples is going to determine the frequency, the maximum frequency that we're going to be able to capture, all right, and the number of bits that we're going to be using in order to represent that amplitude. That is essentially our quantization, all right. In fact, the rate at which we take samples, all right, to record that particular sound, that is known as the sampling rate, all right. In fact, according to a law stipulated by a scientist with his last name being Nyquist, all right, the maximum frequency, all right, that you're going to be able to capture, all right, is going to be half that of your sampling rate. Therefore, if you are trying to capture um, a 20 kilohertz signal, all right, you would need at least 40 kilohertz in order or 40 kilohertz sampling rate, essentially. Okay, because the maximum frequency that you would be able to capture with a 40 kilohertz sampling rate is 20 kilohertz. That is one of the reasons why the sampling rate used on CDs is actually 44,100 hertz. All right, or 44.1 kilohertz. Okay, it is slightly higher than the 20 kilohertz threshold. In fact, humans tend to hear between 20 hertz, all right, at the low end, and 20 kilohertz at the high end. Obviously, this range varies from person to person, and it also varies across the lifespan of a person. All right, the older you get, the probability is that the higher frequencies you will be able to hear less and less and less of, because of the amount of wear and tear that your inner ears might have gone through. And if somebody had worked in very loud environments in the past, then probably it would be the case that there would be even less frequencies that they can actually hear from the high end, probably. All right. So, essentially, at every time interval, as I was saying, what we would do is we would try to capture a value, all right, for the amplitude at that particular point in time. Now, it might not necessarily be the case, as you can see from these dots, that the precise amplitude is going to be captured. That is because the stored value is going to be dependent on the amount, all right, of quantization that we actually have. In fact, there is what is known as a quantization error, all right, and to keep it simple, all right, and to have sort of like an analogy with color, if you remember, if you're only using, for example, 8 bits, all right, the with 8 bits quantization, that basically means that you can only record 256 different levels of amplitude. Okay, kind of like how you would have 256 different colors on your computer system. If you increase the amount, all right, of bits that you're using for quantization, obviously um, um, the amount of accuracy is actually going to go up because you're going to have a lot more different levels that you can actually that you can actually associate a particular amplitude with. All right. Um, uh, in fact, if you have very low number of bits used for quantization, you're going to increase your quantization error, which in turn, if you had to play back the recording that you might have captured, that would cause what is known as a quantization distortion. In fact, it manifests itself as a form of noise, all right? Very similar to the type of noise that we are used to in analog signals, but essentially you're distorting the sound and you're not faithfully capturing what has actually been recorded. All right. So it might be the case that if this black line here is your original audio source, then this orange block is essentially what you've managed to record. All right. Obviously, if you have more different levels over here for the quantization, then the more precise you can actually be, and the closer you can actually get to the curve that you have over here. In a similar fashion, the if you increase the number of samples that you actually take, so essentially here, then the more values you will be able to get intermittently. So, for example, in this case, all right, at this point here, you're recording this audio sample here. At this point here, you're recording this audio sample here. However, this peak here, which sort of like is happening between these two audio samples, is not actually being captured. So if you would need, or if you want to actually capture this sort of like peak that we have over here, you would need to increase the amount of samples that you're actually taking. Is this clear, guys?
Yes, yes, and it's clear.
Okay. So, in fact, if we had to take a look at CD quality audio, all right, the amount of quantization that is actually used for CD technology is 16 bits. That basically means that in terms of amplitude, you have 65,535 different levels of quantization. All right. In recording, um, studio recording booths, you would typically find quantization levels going up to 24 bits, essentially giving you 16 million or 16.7 million different levels of quantization that you can actually capture. Obviously, then when you're porting it down to a CD, you would then uh, approximate that particular value. The reason why they do that is so that you would have as close to a raw file as possible. All right, kind of like how photographers will tend to work with raw images and therefore the larger file formats. Um, uh, Audio technicians will tend to work with raw audio files, and then when they actually produce it to be replicated, they would essentially degrade the audio quality that they're actually sharing to those people. Obviously, the more bits you're using in order to store each and every amplitude sample, the more the more data you're actually going to need in order to store that particular file. All right. So essentially, when we're talking about say CD quality audio, all right, that is using 16 bits of quantization per channel. Now, CD quality audio is actually dual channel. It's a stereo sound. All right, you have the left and the right. All right, so you have 16 bits for the right channel and 16 bits for the left channel. All right, you have 44,100 hertz. So essentially, if you had to calculate it, all right, for a single second, all right, so you would have the following. So you have 44,100 samples per second. You're multiplying that by 2 bytes, which is 16-bit, and you're multiplying that by 2 again for one for each channel, all right, left and right. That gives you the amount of bytes that you're using in order to store 1 second of audio. If I had to divide it by 104, that would give us kilobytes, and that would give us megabytes. So you have 0.16 or 0.17 megabytes per second of audio. If you had to take into consideration a typical song, which is, I don't know, 3.5 minutes long, all right, then we're talking about um, about 500 kilobytes or 600 kilobytes, there or
Most,
thereabouts.
most times 6, 12, 18. 180 plus.
This is sorry. This is those are per second. Sorry.
Uh-huh.
So I'll need to multiply that by 60 by 60 by 60. Sorry, just by 60. So that would be about 35 megabytes per 3 minutes, 3.5 minute soundtrack, essentially. All right, which is in turn one of the reasons why on a disc you would be able to store at most 20 songs uncompressed, all right, in WAV format. If you like songs which are a bit longer, all right, say, I don't know, Stairway to Heaven kind of length, 8 minutes, 9 minutes long, all right, then probably that figure would actually go down to maybe what, 8, 9 tracks on a single disc. In fact, the one reason why CDs were actually 700 megabytes was because 700 megabytes is relatively the same as 60 minutes worth of audio, essentially. Okay?
Yep, thank you.
All right. So, obviously, the amount of quantization that you're going to have, as we said, is going to determine the quality of the overall audio that you're going to have. All right. The higher the bit rate, the larger the file size, the smaller the errors, the less distortion you're going to have, and the better overall sound quality. Conversely, all right, if you have a lower bit rate, you're going to reduce your file size, all right, but your errors are going to be larger, you're going to have more distortion and poorer quality. Another factor that obviously plays into the file size is going to be the amount of samples that you're going to be taking per second. In fact, if you take into consideration the telephone system, all right, on a telephone, the voice that you're using might not, or the voice that is actually being recorded and therefore sent to the other person on the receiving end, might not necessarily be as close to or have a higher fidelity as you might imagine on the other end. In fact, that is one of the reasons why children tend to sound like their parents, especially after they've gone through puberty, essentially. And you get confused. So, for example, I tend to sound quite a lot like my father on the phone. All right. In that case, you can get a lot of confusion. The reason is because our voices tend to have very specific frequencies, all right, that make our voices our own. In fact, we call that the timbre of our voice. Okay. However, every person has a different timbre, all right, of their own voice, which is determined essentially by the different frequencies that are being uh, broadcast essentially every time we speak. All right. Now, if you these frequencies tends to be on the higher end of the spectrum, all right, which in turn gives us our sort of like audio fingerprint, all right. However, on the phone, all right, the maximum frequency that is actually captured, or rather the sampling rate that is used in order to record telephone calls, is around 8 kilohertz. So essentially, the maximum frequency that it can actually capture is up to 4 kilohertz. But our timbre frequencies, or the frequencies that make our voice our own, those tends to be towards the higher end of the spectrum. Thus, what results in that little bit of confusion that one might experience on a telephone conversation. All right. So we've talked about sound. Let's talk a little bit about video. All right. So when we talk about video, all right, video is sort of like a combination of both storing images as well as audio. All right. In fact, when we're talking about movies or video, we're really and truly talking about a series or a sequence of still images that need to be played once after each other. All right. And most modern videos can be made up of thousands of these still images. All right. In fact, if you had to go to a cinema, all right, whereby they want to showcase, all right, the highest quality picture possible, all right. If you go to a digital cinema, the films that they actually showcase are stored in their raw format again, and they tend to eat up huge chunks um, of of data. So, in fact, if you think about it, most movies, all right, especially the higher definition movies, those are captured at 60 frames per second. If you're talking 3D, that's 90 frames per second. All right, so that's 90 images that you're storing per second for that particular movie. If you're talking about a cinema quality needs to be quite dense in terms of number of pixels. All right, so it's probably somewhere in the region of 8K quality. All right, so 8K quality times 60 or 90, depending whether or not you're talking about 3D or not. And then over and above that, you also need to store the audio that goes along with that. All right. And probably not in stereo mode, but probably in surround sound as well. All right. So for each and every individual speaker, you would have your own channel as well as your different types. All right. So if you have a 7.2 surround sound system. All right, you have 7 speakers, 2 subwoofers, and you have a channel for each and every one of those. So you can imagine that the amount of data that you actually need to store at any given point in time is going to grow and grow and grow and grow. All right. So this is why it is very, very, very important. All right, especially for us to be able to consume video. All right, that we would have forms of video compression. All right. In fact, you might see, all right, video formats, and especially with these high definition televisions, you'd see that the resolution would be, for example, 1920 by 1080, P60. What does that mean? It means that you have 1920 pixels in the X direction, 1080 pixels in the Y direction. P basically means that you're using progressive images, where basically the entire image is actually being replaced, all right, rather than having an interlace system, all right. Sometimes you have either P or I, all right. I means it's interlaced. Interlace means that essentially between one image and the next, they would literally convert half of the pixels, all right. They might start with the odd lines of pixels, and then they would convert the even lines in order to reduce the load on the CPU that is actually displaying the image, all right, to exactly half the amount of pixels at any given point in time. And 60 is the number of frames per second, all right. Yes.
Why is 1080p? Why does it look crisper than 1080i? Because it's technically still the same number of pixels per.
Mala. So imagine, all right, a 1080p picture basically means that you are going to get, all right, a full new image, all right, every frame. Okay, so every frame is going to change all of the pixels.
Esatto.
All right, a 1080i image is going to change exactly half of the pixels. So in this frame, it might only change the odd pixels. All right, and the next frame is going to change the even pixels, and then so essentially you're getting a blur. All right, between the previous frame and the current frame. All right, whenever you're viewing any frame whatsoever.
There's a bit like spillover, kind of.
Exactly, and the reason why they're doing that is because essentially you are reducing literally the number of pixels that you would have to give a color to by half. In fact, those kinds of televisions tend to be a lot cheaper, you know, and then they're older as well. And nowadays, they are no longer available. However, in the past, it was a genuine decision that people had to do. This is going to be a 1080i image or a 1080i television or a 1080p television, you know. And there was a big price gap. Nowadays, the price gap is not because of these types of resolutions. The price gap is actually television, given the shortage of silicon worldwide. But that's a different story altogether. That's all electronics.
It makes a lot of sense now, because a few months ago I found out that, do you remember Gran Turismo 3, the one on PS2?
Yes.
That could run at 1080, and I couldn't understand how the PS2 could process 1080 on, what's
In fact,
CPU, that makes sense.
At the time when this was actually coming, I used to work at Exotique a long time ago, where I used to sell a lot of games for Xbox and PlayStation. And one of the things that we used to showcase was also the fact that PlayStation at the time, even though it was a superior machine in terms of its sheer hardware, it was also very complex. And therefore, game programmers weren't actually able to make use of the entire potential of the machine. And if you actually look at the back box of the game, you would actually see the resolutions that it could actually go up to. And it was always 1080i. If it went up to 1080, most of them went actually to 720 actually.
Yeah.
But the Xbox equivalent, so the same game but for Xbox, all right, since it was running on a more simple architecture, they used to go up to 1080p, no problem. You know, and sometimes when people used to not know which system they were going to go for, tell them this is a reality. Are you going to go for one or for the other? and then they would choose. It depends on the individual on that. But yes, it's something that one needs to take into consideration. Nowadays, the more important aspects that we take into consideration are, for example, the contrast ratios, whether or not it has HDR enabled. Nowadays televisions have become their own computers in their own right, essentially.
Yes.
Right. So let's talk a little bit about video compression.
Thank you.
When we talk about, you're welcome. When we talk about video, all right, in general, all right, video contains a lot of redundancy, both in terms of spatial redundancy as well as temporal redundancy. What does this mean? Spatial redundancy basically is redundancy that exists in each frame. Essentially, each frame, all right, is going to be made up of very, very, very small differences, especially when we're talking about pixels which are very close to each other. All right, pixels which are close to each other are generally speaking going to have very similar colors. All right, so that is what is known as spatial redundancy. Temporal redundancy basically means that each frame, all right, tends to be very similar to the previous frame and the frame that's coming next. All right. So what we can do, all right, is we can make use of both of these factors in order to help us encode movies, all right, or encode films in a much more space efficient manner. It does not necessarily mean that it's actually going to be high quality. You might actually get aberrations and you might get some weird effects within within these kinds of compression within these compression techniques, because obviously once you've compressed them using the technique that we're going to be discussing, all right, you would obviously need to decode it, and what it's decoding, all right, when you're playing back might not necessarily be equivalent to what you have recorded in the first place. All right, so you might have lost certain data because of this encoding process. MPEG does this form of video, is one of the formats of video compression that there is out there. All right, how does MPEG work? So essentially, MPEG uses what is known as keyframes. All right, in order to store the more important images of the film, all right, or of the video that you're trying to capture. Essentially, you would make use of a number of these keyframes, all right, in order to then predict, all right, what are going to be the intermittent frames, all right, or the frames in between the keyframes, all right. This is obviously done by certain algorithms in the background, all right. So obviously, upon encoding, you need to identify which keyframes are going to be the more important ones, and you're also going to determine how you're going to be able to predict the other frames, all right. In fact, MPEG tends to make use of three different types of frames. You have the keyframes, all right. Then you have what are known as the predictive pictures, all right. And then you have what are known as the bi-predictive pictures, all right. So the keyframes are the frames that are actually stored at certain intervals, all right. The predictive frames are frames that are going to be predicted based upon the previous frame that came before it. All right? Or the previous few frames that came before it. So it is predicting what is going to be the next frame, all right, based upon previous frames. The by predictive pictures, or the B pictures, are pictures which are not only made up of pictures that were predicted with frames that came on before, but also frames that are coming after. So essentially, if we had to take a little bit of an example, all right, this would be a keyframe. So in MPEG quality, you're actually storing the full data of that particular frame. From that, you would determine what your next predictive image is going to be, and a B frame, all right, will make use of the previous frame as well as the next in order to determine what needs to be played, essentially. And you might have a sequence, all right, of how these frames should be or are stored underneath. Okay, so wherever you have an I, that essentially determines that you have a keyframe. A P means that you have a predictive frame. B is a bi-predictive frame, all right, and so on and so forth. All right, so essentially the decoder would know which frames are, for example, the keyframes, all right, and from those you would actually get you would be able to decipher then, obviously using the codecs underneath to decode what the P frames and the P pictures and the B pictures need to be as well. You understand? I'm not going into the algorithm of it per se, because obviously that is beyond the scope of this program. But beyond the scope of this course. But essentially, what I wanted to sort of like point out to you is that this is one of the ways that we can actually compress the amount of data that we need in order to store video. All right. Any questions so far?
naħseb li
Thank you.
Okay. So that is essentially, what we had with regards to data representation for audio and movies. What about alphanumeric data? So essentially, when we talk about alphanumeric data, we're literally talking about characters, all right? Characters that represent numbers, characters that represent letters, all right? As well as special characters that might mean certain special commands in the computer, all right? In fact, every computer that exists on the face of the planet makes use of what is known as a character set. The character set basically determines the characters that can actually be represented by that computer. One of the main schemes that was actually used in the past was what was known as the ASCII character set, all right, or also short for American Standard Code for Information Interchange, all right. The original ASCII character set had 7 bits used for the character codes themselves, and 1 bit was used for parity checking. All right, essentially, it basically was used in order to determine whether or not there was some form of error in the encoding of that particular character. Essentially, it used to count whether or not you had an odd or even number of ones in your character, all right? And if it was odd, it would be 1. If it was even, it would be 0, essentially. And if there was a mismatch between the parity and the number of ones that you would have within your character, then you would say there has been some form of corruption here, essentially. All right. That is assuming that obviously only 1 bit was actually changing. It's not a perfect system. But with the original ASCII character set, essentially, since you only had 7 bits that were used in order to represent these alphanumeric characters, you only had 128 different characters, 128 different characters to play with. Okay, and these are the characters in question. All right, notice that we have a number of special characters. All right, such as the null character, the end of transmission character, for example, the synchronization character, the bell. This is essentially a command that you use to send to the computer in order to play a beep. Because on most motherboards you actually have a speaker inbuilt on the motherboard itself, and the first type of sound that you used to have was actually these forms of beeps that used to happen from these kinds of commands. And then you have your your punctuation characters, your alphanumerics, all right, as well as your alphabet in both uppercase as well as lowercase, as you can see over here. The good thing about the ASCII set was that all of the characters were sorted in order. In fact, the character for capital B, for example, was exactly 1 value higher than the value for A. All right. In fact, this is one of the reasons why, or as you can see, character B has the value 66, whereas the character A has the value of 65. All right. C, all right, is 67, 1 more than B. All right, and so on and so forth. The main advantage of this was that essentially underneath every character that we're talking about can be represented as a number, all right, and that characters that have some form of order, especially with regards to the alphabet, all right, they were also ordered sequentially. It was also very easy to be able to translate from, for example, uppercase to lowercase. All you would need to do is you would need to take the uppercase character, all right, and add 32, all right, in order to get the lowercase character. So 65 plus 32, all right, will give us 97, all right. 66 plus 32 will give us 98, and so on and so forth. Conversely, if you wanted to convert from lowercase to uppercase, you would do obviously the opposite. All right. As we also mentioned, all right, the ASCII character set also had control characters, all right, which were predominantly used in order to send instructions, for example, to the screen or to a printer or through a network, all right, in order to basically tell that device, for example, to skip a line or that, for example, you're finishing your transmission, all right, with the end of transmission character, for example, all right. Or you could also have characters which signify instructions, such as the bell instruction, which literally would sound a beep on your motherboard, as we had mentioned earlier. All right. Now, as you can imagine, all right, this 128 set of characters, all right, was not really enough in order to represent all of the different types of characters that one might imagine. It's very good if you speak English, but not everybody on the face of the planet speaks English. All right. So what they did was they created what was known as the extended ASCII character set. All right, whereby they got rid of that parity bit character and used the full 8 bits in order to be able to have more expressive a more expressive character set. All right. In fact, by just adding that one additional bit, we've extended from 1 to 8 characters all the way up to 256 different characters. Again, this was quite good for those languages that were similar to those which were English-like, essentially. All right. In fact, this is what the extended character set looks like. Notice that the character set, all right, up to character 1 to 7, all right, was exactly the same. All right. This was actually what was added later. So as you can see, you get, for example, characters which have additional accents upon them, all right, in order to have more expressivity. However, even this, all right, type of character set does not have the expressive power to represent all of the different languages that we might have on Earth, all right. So essentially, how were characters actually decoded? So essentially, you would have your binary sequence. You would take each 8-bit clump as they were, all right. You would decode them into numbers, all right, and then you would take each number, look it up, and see what that is. So, for example, 79 is capital O, 110 is N. And so on and so forth. All right. So essentially, you would take each 8-bit code, convert it into a number, and then convert that number into the character. All right. That it is represented. You might actually have something like this even in an exam situation where you're given, for example, a character sequence. You might be asked to convert it into binary using the ASCII character set, or vice versa. All right. In fact, over here you have another example. All right. For example, you have this sentence over here. Right. How would you convert it? You will essentially do the opposite. Essentially. All right. It is quite a mechanical process, as in you take for it what each character code is, and then you would convert it into binary, kind of like how we used to do binary conversion of unsigned integers in Introduction to Computer Architecture. You are not expected to know the ASCII character set by heart, obviously not. All right. The ASCII character set in that case would actually be given to you. All right. Is this clear?
All right,
Yes.
thank you.
Thank you.
All right. Right. As we mentioned, ASCII is not the only form of alphanumeric encoding that actually exists. There also exists the EBCDIC character set, all right, which is essentially the extended binary coded decimal interchange code, which was developed by IBM, all right, and it was essentially a character set that was developed for IBM made machines. In fact, this is the IBM or the IBM character set essentially that was developed. As you can see, the notion is very, very, very similar. All right. In fact, the original EBCDIC character set, all right, made use of 7 bits, just like the ASCII character set. However, there was a bit of of confusion, especially when you got computers which were developed to work with the ASCII character set and other computers which were developed in order to work with the EBCDIC, all right, character set. There were some characters which were similar to each other, so certain codes mapped to certain functions. So, for example, null, all right, for both the EBCDIC character set and the ASCII character set was the same value, right? But then there were other characters which were completely and utterly different, all right? So, say for instance, I don't know, the delete character for the EBCDIC character set was number 7, whereas for the ASCII that essentially was the bell, all right, command. So obviously this threw up a lot of problems when it came to having these two different computers working with these different character sets communicating with each other. This is why a different form of character set was developed. It's known as the Unicode character set, all right, which is short for Universal Character Encoding Standard, all right. Essentially, it makes use of 16 bits of encoding, which essentially gives us 65,536 different characters that we can actually represent. In fact, there are yet other Unicode standards which go even up to 32 different bits, 32 bits, which gives us even the potential to represent even emojis and historical symbols such as hieroglyphics as well, even with that character set, because like that with 32 bits you can actually represent 16.7 million different characters, all right, such as Chinese, all right, hieroglyphics as we mentioned, all right, as well as other other characters such as Arabic and so on and so forth. All right, and like that, you would actually be able to represent all of the different characters. In fact, nowadays it's pretty much standard. All computers tend to make use of Unicode. All right, whether it's 8-bit, 16-bit, or 32-bit, in order to aid communication between these different types of computers worldwide. Any questions with regards to this topic?
So far, so good.
Shay.
Yep.
All right. Okay, cool. So that brings us to an end with regards to data representation. All right. What we're now going to be talking about, or shifting our focus towards, is cache and how we can actually make use of cache. All right, or caching essentially as a means to enhance the performance of our computers. All right. Essentially, all right, when we're talking about computers, all right, and if we look at the architecture of these different computers, you'd start to realize that there are a number of bottlenecks which prevent us from making the full use, if you will, of the speeds that our CPU can actually achieve. All right. In fact, the clock speed of our CPU can run at a very, very high rate, but all of the other devices that are connected to our computer, all right, with a possible exception of your GPU, all right, those tend to be running at slower speeds than that of the CPU. In fact, that is one of the reasons why we've introduced cache memory. All right. Essentially, the problem that exists if we were not to use cache, for example, is that the CPU would be running on a particular frequency, but our main memory would be running on a much slower frequency. And obviously, they would be communicating over a bus. So essentially, you might have a CPU running on a specific number of gigahertz, but your main memory, all right, would be running on something which is much slower than that. So, for example, nowadays it is quite possible for each and every core on your computer, all right, to run at around something like 4 gigahertz each. All right, it's pretty much standard nowadays. But most RAM modules, all right, would only be able to operate at, say, 3.2 gigahertz. All right. So as you can see, our RAM is already not as fast as our CPU. All right. Notice it is not as fast as a single core. All right, and only one core at a time would be able to access main memory at any given point in time. So if you have 4 cores or 8 cores or 12 cores or whatever, all right, you are seriously bottlenecking the performance that your CPU can theoretically achieve, all right, when communicating with main memory, all right. Also have to take into consideration that there are different kinds of main memory, all right. You have what is known as SRAM, and you have what is known as DRAM. All right. The S stands for static, whereas D stands for dynamic. All right. Static RAM is more expensive RAM. All right. Essentially, static RAM means that once you set the values, all right, to that, so you set a particular value to that RAM module, all right, as long as there is power being supplied across that particular module, it will keep the data without the need of being refreshed. In fact, dynamic RAM sort of leaks charge. So periodically it needs to be refreshed, all right, in order to keep the data, all right, which means that SRAM is faster, whereas dynamic RAM is slower, all right. However, most RAM modules that we actually plug in to our motherboard is actually made up of dynamic RAM, all right, because they're cheaper, thus allowing us to, with the same amount of money, have more in terms of capacity, so more RAM. So this is where cache memory comes in to play. So cache memory essentially is memory, all right, that sort of like sits in between the CPU itself and main memory, all right. And cache memory is a small chunk of memory, all right, that works at literally close to the same speed as the CPU, all right, in order to aid, all right, the use of the CPU to reach its full potential, all right. However, the CPU is not actually aware that cache memory is actually there. It is sort of like hidden. In fact, that's where the term cache comes from. All right, it comes from the French term cacher. All right, which means to hide. All right. In fact, with the with the use of cache memory, we can actually bridge the gap, all right, between our RAM modules as well as our CPU. All right, and this, mind you, this performance gap is actually getting bigger and bigger and bigger, depending on the number of CPUs that we're actually, or the number of cores that we're actually integrating in each CPU that we actually have. All right. How does cache memory work? Well, that's essentially what we're going to be discussing in these set of slides. So first and foremost, cache memory makes use of what is known as a locality principle. It is something that we see within applications that we can exploit in order to make our computer run faster. There was somebody who was about to ask a question, I assume.
Yep. Yes.
Right.
On the previous slide, so you said
Okay.
that because the CPU is getting quicker,
Yes.
and because we have more cores running at higher frequencies as well, we
Yes.
need cache memory to bridge the gap between the RAM and the CPU. But kind of in parallel to a multi-core CPU, we can have multiple RAM modules running at, say, if it's DDR4,
But
it will go beyond 3000 gigahertz. Oh, 3 gigahertz.
yeah, true. The problem is that each core is only going to be able to communicate directly with any one of those. So essentially, a core,
Still a one-to-one.
it's still a one-to-one. So one core is going to be making use of the bus, of the system bus. All right, you cannot
Okay.
have multiple cores making use of the system bus at the same time. You know,
Because you technically need a dedicated system bus per core, theoretically.
because each there are ways of improving Ġifieri,
They do.
but what I'm trying to point out is that that essentially whenever a core is if you remember back to when we were talking about the read cycle and the write cycles.
Yeah.
All right. Essentially, what a core is going to do is going to needs to make use of the address bus and the data bus as well as the control bus in order to identify whether or not the data that has actually been written has been written to that particular location. All right. So you would need all three, which is essentially your entire system bus. You understand?
Yes.
Now, what we can do, all right, in order to speed things up, all right, is to make use of multiple channels in order to say, all right, certain cores will be using certain channels only. But again, this is not the default state of every computer because not every computer has multiple channels.
Yes, you can run single channel DRAM if it's what we're talking about.
Exactly. So your motherboard does not necessarily have that capability.
Exactly. Okay.
And your CPU in turn does not also automatically have that capability.
Exactly. So they have to factor in single channel DRAM because that's the the minimum amounts needed, and that's potentially what you will be running. So you can't.
Exactly. So we're
Playing it safe.
moving in that direction, Tajifir, where everything becomes multi-channeled, etc., Tajifir. But
Yeah.
currently, it's still not the case that you have to have multi-channeled RAM or you have to have, that's not the case. So the CPU performance gap is still something that is quite quite a big factor in performance. All right, and then this is where cache memory is actually going to be of a big help. Okay.
Thanks.
All right. So I was mentioning the idea of the locality principle. Essentially, what I mean by this is that whenever you're running a program, okay, essentially the locations, all right, that you're trying to access in order to read from or write to tends to be what are known as highly clustered zones, all right, and this can be this is because most programs tend to run in loops, all right, or tend to make use of the same variables or the same data locations for an extended period of time, all right. In fact, um, uh, we tend to see that data is quite highly clustered, all right, and it's not really randomly distributed across your entire RAM module or your RAM capacity. They tends to be quite highly clustered, all right, and they fall under two locality references, all right, that we can make use of to exploit, all right. The first locality principle that we're going to be looking at is the idea of spatial locality. Essentially, what this means is that the instructions that we might need to fetch, all right, for the next step in the process tends to be probably within the same location in main memory as the previous instruction. This is because most applications tend to spend a lot of time in loops, all right, which essentially means that the instruction that you're going to be executing next is going to be literally the next instruction on the next line of code, if you know what I mean. All right, which means that you're constantly going to be fetching an instruction in and around the same area spatially. All right. Another one is known as temporal locality. What does this mean? Since we spend a lot of time in loops, it means that we're making use of the same data points or the same variables over and over and over again. So we tend to look at the value of that particular variable, tweak it, modify it, but we're constantly making use of those particular variables. Therefore, um, uh, a memory location that you might have accessed recently might be a memory location that you're going to access again in the near future. All right, that's essentially the idea. So with spatial locality, all right, what we're saying is that if you access this particular location at this point in time, then it's going to be highly probable that you're going to access another memory location very, very, very close to that location that you might have already just accessed. Temporal locality basically means that if you are accessing this location at this particular point in time, then it's going to be highly probable that you're going to be accessing that same memory location very, very soon in the near future as well. All right. So making use of these two forms of locality, all right, these two principles of locality, we can take advantage of that, all right, and make our cache memory, all right, take advantage of this so that we can actually access this data a lot faster, all right. How do we do this? Well, we introduce this cache memory. Essentially, the cache memory, as I said before, exists as a transparent entity between the CPU and main memory. In fact, the CPU is not aware that there is this cache memory involved. All right, as far as it is concerned, it is communicating directly with main memory. However, this cache memory is a sort of area all right, a small area of memory where you would be able to store, all right, values, all right, from main memory intermitted in this particular location. Essentially, when the CPU is looking for a particular piece of information or a particular instruction that is found on main memory, what the computer first does is it checks to see whether or not it is in the cache memory first. If it is there, that is known as a cache hit. All right. If it is not there, then essentially it is then retrieved from main memory and then stored in cache memory intermittently. All right. So essentially, if there was a cache miss, all right, then essentially you would retrieve the data from main memory and then you would probably store that data in cache memory so that you would make use of that locality principle that we were talking about earlier. All right. Now, the whole point behind cache memory is to make sure that the hit ratio or the cache hit ratio of cache memory is as high as possible. All right, it is not outside of the realm of possibility to have cache hit ratios which are as high as 90%. All right, so in that way, you're actually working a lot faster. All right, when you're actually communicating between CPU and main memory. All right. So, how is this cache memory organized? Essentially, you would have a piece of hardware, all right, known as the cache controller, all right, and the cache controller would be organized into a number of equal sized slots, all right. They're typically either 8 words long or 16 words long or 32 words long. It depends obviously on your cache controller. When we say word, all right, we're talking about number of bits that the CPU can actually handle at any given point in time. So essentially, when we're talking about an 8 word slot and you have a 32-bit computer, you can have 8 32-bit, all right, words stored in one slot. Okay, essentially, you have a copy, all right, of what happens to be already in main memory, all right, on your cache. So that your computer, instead of going to main memory in order to retrieve this information, it will first and foremost check to see whether it's in cache. If it's in cache, it will retrieve it, and it will retrieve it at near CPU speed. If it is not there, then it then will retrieve it from main memory. Okay. In fact, if you had to take a look at it visually, all right, you would have your cache, all right, which have a number of slots, okay, and each slot would correspond to a block of memory that you have over here. So in this case, block number 3 of main memory is stored in slot 0 in cache. All right. Now, a very important thing to note is that each cache slot will also have a number of other bits that would actually be able to which are used in order to identify certain things. First and foremost, it has what is known as a valid bit and a dirty bit. A valid bit essentially is a bit that is used in order to determine whether or not this block in memory is still valid to be stored within the cache. All right. Ideally, all of your cache blocks, all right, or all of the slots that you would have within your cache would contain blocks which are valid. If they are invalid, then you would swap them out for a different block. Okay. The dirty bit, on the other hand, all right, that is used to identify whether or not some modification has happened on the block within that particular slot. Meaning that if, for example, if this dirty bit is on, all right, then essentially what that means is that this block tree that we have over here and this block tree that we have over here are different. Then essentially what that means is that we would need to, at some point, take this data that we have over here and replace it with the data that we have over here. Why? Because the data that we have in cache over here is by far more updated than the version that we have over here, if you understand. All right. And finally, you would also have a set of bits known as your tag. Essentially, the tag is what is going to be able to map, all right, the slot with the block itself. So essentially, this tag is going to be able to map that at slot 0, in this case, we're referencing block number 3. So far, so good, guys?
Yes.
All right.
Yep.
Okay. So that is obviously an overarching ideology of how cache memory is organized. All right. However, there are different ways that one can map cache memory, all right, to main memory. All right. So we're going to be looking at a number of different scenarios. All right. The first mapping scenario that we're looking at is what is known as associative mapping. All right. So let's assume, all right, for the sake of argument, that we are making use of a 4 gig sized main memory. All right. So 2 to the power of 32. And let's assume that main memory, all right, is going to be divided into blocks of 32 bytes each. All right. So each block has 2 to the power of 5 different words. All right, stored within them. Okay. Then that essentially means that we're going to have 128 million different blocks in main memory. Why? Because if you had take 2 to the power of 32 and divide it by 2 to the power of 5, you get 2 to the power of 27. Okay, so you have 2 to the power of 27 different blocks within main memory. With associative mapping, all right, what you would have is that each slot within cache memory can, technically speaking, be mapped to any other block within main memory. All right, so slot 0, all right, can have a copy from block 0 all the way up to block 2 to the power of 27 minus 1. All right, same as slot 1, same as slot 2, same as slot 3, and so on and so forth. All right. So essentially, every slot can be mapped to every block that you have within main memory. All right. In order to be able to have this associative mapping, all right, your cache, all right, let's say that our cache, in our case, has a size of 512 kilobytes, all right, that can be divided. That needs to be divided in exactly the same number or the exact same size of block that you would have within your main memory. So if each block in main memory is using 32 bytes or 2 to the power of 5 bytes, then essentially each slot would need to be of the same size. Therefore, the number of slots that you have within cache memory, all right, is going to be equal to 2 to the power of 9 divided by 2 to the power of 5, which is equal to 2 to the power of 14, which is roughly 16,000 different slots, or 16,000 different lines that can actually map each slot to each and every other cache block, main memory block, essentially. All right. So that is essentially what fully associative mapping is actually going to allow us to have. All right. Now, as we mentioned, with respect to associative mapping, you will also have the valid bit and the dirty bit, which work exactly in the same way as I explained before. So the valid bit is in order to indicate whether or not the data stored within the slot is identical to the data stored within the block. All right. If not, then you would need to copy, the valid bit is in order to determine whether or not the block that is stored within the slot is actually needed, all right, within cache memory. If not, you would swap it out for something else, all right. So essentially, how would you know whether or not it is a valid bit or not? Well, is that particular block that you're storing within that slot of a process that you're currently running? If yes, then probably it's valid. If not, then it's invalid. So you'd swap it out for a different block. All right. And the dirty bit, on the other hand, is the bit that keeps track whether or not the data that is stored within the cache is identical to the data that is stored within main memory. If not, then probably you would need to copy it over at some point. Okay. So another thing that you would also need to have with associative mapping is that you would need to have a 27-bit tag field. All right, that tag field, all right, or those 27 bits for your tag is going to be able rather the bits that you're going to be using in order to identify which which block rather that slot is actually referring to. And you would also have another additional 5 bits, all right, in order to identify which word you are actually making use of, all right. So remember that each block, all right, is made up of 5 words because we have 32 bytes, okay. So essentially, we're asking which byte out of those 32 bytes are we actually going to try to manipulate, or we're going to try to read. That those 5 bits are used in order to be able to identify those. Is this clear?
Yep.
All right. So essentially, with associative mapping, this would be the overall structure that you might see in this type of computer. All right. Yes, we already talked about this. So essentially, what would happen is that when you are trying to access a particular memory address, all right, the cache hardware will intercept that address. It will use that reference in order to search whether or not that memory address, all right, is within main memory, all right, within the cache itself, all right, by using the tag, all right. It will identify which byte we are making use of by these 5 bits, all right. It will perform its manipulation. If it's changing the data within that cache slot, then it would first and foremost, if it finds it, it would have a valid bit of 1. It would make sure that that slot has a valid bit of 1. If it manipulates it, it might change that dirty bit to 1 to indicate that is now been tampered with. All right. Now, obviously, the whole premise behind cache memory is that this needs to be as fast as possible. So it doesn't need to actually check each and every slot one by one. It's actually doing all of these checks in parallel. That is what is so powerful behind it. So you would literally check to see whether or not that memory address is stored within cache by literally looking through all of the tags at the same time. This is why it becomes a lot faster. All right. If it is valid or if it is present, then you would be able to read it from main memory. If not, you would retrieve it from main memory. So let's give an example. So let's say that we're trying to access memory location given by this hexadecimal notation. This, if you had to convert it into binary, would look something like this. The first 27 bits will be used in order to for us to identify the tag. The last 5 bits would be used in order to identify which word. So essentially what we're talking about is we're working with word 10100, all right? Since we're talking about computing, we tend to convert this into a byte, all right? Because that is the smallest amount of data that we can actually manipulate at any given point in time. And we're working with slot 010, 000, 00, whatever. All right, this entire number. All right. So essentially, if you had to convert this, okay, into hexadecimal notation, it will be this one over here. Okay. Now, what are the advantages and disadvantages of this fully associative mapping cache? Well, the first main advantage is that essentially every block in main memory can be allocated to every cache slot regardless of its location. All right. This makes it obviously a lot faster and much better, all right, because essentially it also works well, irrelevant of how regular the data or the how big the program is, all right. Essentially, you can store a number of slots or a number of blocks or slots in slots in cache. However, in terms of disadvantages, all right, this is quite expensive, all right, because there is considerable overhead, all right, in order to be able to map each and every block into any slot that you have within your cache. And it also requires that you have a mechanism to be able to search through all of your slots in parallel via the tag mechanism. All right. So that is obviously a little bit of an overhead that you would need to take into consideration, obviously upping the price of this form of mapping. Was there a question? I thought I heard somebody asking or about to ask a question.
I may have hit the space bar.
All right. Okay. Fair enough.
Sorry.
Okay. No. I thought I was speaking over somebody. Didn't want that to happen. So that is one type of cache mapping. All right. Another type of cache mapping is what is known as direct mapped cache. Essentially, if we take a very similar situation, i.e., main memory of 4 gigabytes, all right, where each block is divided into 32 bytes, all right, and that means that we have 2 to the power of 27 blocks in main memory, all right. What we could do, all right, in turn, is make each and every slot that we have in our cache memory only be able to store a subset of these blocks. All right. In this case, all right, we are going to explicitly state that each slot can correspond to a number of blocks. All right. In this case, each slot can have any of 2 to the power of 14 different blocks. All right. So the way that, or rather 2 to the power of 13, sorry. How did 2 to the power of 13 come about? If we have 2 to the power of 14 different slots, all right, what we want to do is we want to be able to split these blocks evenly across all of the different slots that we have within cache memory. So how do we do that? 2 to the power of 27, which is the number of blocks, divided by 2 to the power of 14, which is the number of slots, giving 2 to the power of 13, which is essentially the number, all right, of blocks that can be located on a slot. So notice slot 0 would be able to be mapped to blocks 0 up to block 2 to the power of 14. All right. So that is the number of blocks that can be stored within slot 0. Slot 1 will sort of like slightly overlap, or rather overlap it quite a lot. It would be able to store from block 1 to 2 to the power of 14 plus 1. All right. Slot 2 will start from block 2 to 2 to the power of 14 plus 2, and so on and so forth. All right. So as you can see, not every slot, no, rather, every slot cannot actually be mapped to every other block, but it can reference only a subset. All right. Obviously, this would mean that there is less overhead. However, it would obviously introduce a little bit more complication when it comes to how we're actually going to be able to identify that particular block and obviously word. All right. In fact, you would need to make use of 13-bit tag. All right, which is going to be able to identify. All right, which of those blocks, or which of the set of blocks are you actually going to be referencing? All right, is it going to be the first one, the second one, the third one? All right, notice first is going to be relative depending on the slot. All right, you then also need to have 14 bits, all right, to identify which slot you're talking about, and then finally the 5 bits in order to identify the word. Okay, do you understand this, how we're actually splitting this up now?
Perhaps you can repeat the word bit.
Okay, no. This, so essentially what we're saying is, let me just do that. So essentially these 5 bits are exactly in the same way, though, that the word bits were used before. Remember that we're using 32 byte blocks. All right, meaning that we have 2 to the power of 5 different bytes, all right, per block. So far, so good.
Yes.
But we are only manipulating or reading a byte at a time.
From cache.
No, from main memory in general. Whenever we're reading,
okay.
we're always reading 8 bytes at a time, or 8 bits at a time. Sorry. All right. So I need to know, out of those 32 different bytes, which one am I actually manipulating, or which one I'm actually reading.
Okay.
That is basically where this comes in.
All
All right. Now, these 14 bits for the slot, those are going to identify which slot in cache we're actually talking about. all right? And these bits for the tag is going to determine, all right, which block from the set that we can actually read from is going to be the one that we're actually targeting. So if you take into consideration over here, all right, slot 0, all right, the first block that slot 0 can actually refer to is block 0.
Mhm.
All right, the last block that slot 0 can refer to would be block 2 to the power of 14.
Mhm.
All right, in a very similar fashion. All right, the first slot of slot 1 would be block 1.
Mhm.
All right, so essentially these 13 bits is going to determine which out of these, all right, within the set that it can actually map to, are we actually talking about.
As
All
that
right,
establishes the block.
as that these slots, the slot bit is going to determine which slot we're talking about over here. All right, and the word is going to determine which 8 bits we're actually going to be manipulating or reading from. Okay, obviously you would still have a valid bit and a dirty bit, just like in the previous example.
Yeah, because it needs to know which one is in use and
Exactly. All right, so that is essentially what's going on, right?
Okay.
Now obviously this has its own advantages. Okay, this is obviously over here we have another worked example. So imagine if we had this same memory location. All right, we're saying essentially that we're working with this particular word. We're working with this particular slot, as we can see over here, this data coming in from over here, and we are working with this particular tag. All right, that's essentially it. We are literally taking these bits and we're seeing how we're actually going to be mapping them. All right. Now, direct mapped cache has a number of advantages. As you can see, it is more simple in order to design architecturally. All right. So it is less expensive. All right. Since your tags are actually going to be smaller. All right. Then the associative mapping, then you're going to have less hardware overhead. All right, and since essentially you're going to have an associative search, the slot is actually going to be found relatively fast. However, as a disadvantage, all right, what can happen is that you might have a fixed location, all right, within a memory block, all right, that is um, constantly being written to or being popped in and out of cache, therefore increasing the amount of cache misses, all right, that you would have. So imagine if you had a variable in a program, all right, that is is within a block, and that block is constantly being swapped in and out for a different block, all right, for that particular slot. Then it means that every time you come to access that particular variable, the likelihood of you having a cache miss becomes quite high. All right. So obviously, it is not as performative as the associative mapping example that we have seen. All right.
Is it because the CPU is still going?
It's because so let's take into for example, you have to take into consideration that your CPU is going to be manipulating your is going to be running multiple processes at the same time. All right, that's a given. Okay. In fact, what you're if I just take a very quick example. So if I show you my task manager, all right, as an example, these are all of the different processes that are currently running on my system. All of these, all right, would probably be requiring access to main memory at some point, in which case you, um, your cache is actually being used at this point in time. Correct?
Mhm.
All right. So what is probably happening for all of these different processes? All right. If it was using a direct map cache, let's say I had a particular program that is making use of a lot of data within block 0. All right. Notice block 0 is only accessible within slot 0. No other slot in my cache memory using direct mapped cache would be able to access block 0, because block 0 is essentially unique to slot 0. Correct?
Correct?
All right. Now imagine the program in question that is making use of block 0 in main memory also happens to be a program that is maybe not always taking front priority of the other application. So let's say it's not Adobe Reader or Discord, for example. Let's say it's I don't know
Outlook.
the file explorer or something of the sort. All right, which I'm not currently using directly. All right, imagine that I'm always trying to access it. All right, at intermittent times. It's obviously what might be intermittent for a CPU might be very frequent for us, Tajifiri, but try to understand this feature. Imagine that it is not being used that often, so probably cache memory is saying, I'm not going to store slot 0 and keep elements for my file explorer. I'm making predominantly more use of Discord, so in which case I will use I would use the slot predominantly for a block of um, memory that contains elements of Discord. Yes. But then if I come again later and I say, all right, let me try to open my file explorer now. Said, it's no longer there. I have to retrieve it back. So it would introduce a lot more of these cache misses. Essentially, the probability that you would have cache misses would increase because there would be a number of blocks which are only um, uh, uh, accessible, all right, to a subset of blocks at any given point in time. Imagine, another example. Imagine, for example, that I'm running a program which is very resource hungry, all right? Say I like to develop games. For example, I tend to use Unity, and I'm currently working on a very large project. All right, and I'm trying to do something super ambitious. All right, it might be the case that most of my slots, all right, would be used. All right, or a substantial number of my slots would be used in order to um, uh, make use of the blocks that are used by that particular program. However, it could be the case, all right, that the number of blocks, all right, that can be mapped to my cache is much smaller than the amount of blocks that I would actually need, in the sense that there might be a block which might literally just be outside of the range that I can actually store in. So let's say that my program happens to be, all right, running from block 0 to block 2 to the power of 14. All right. So, again, yes, there are going to be a number of blocks which are going to be or a number of slots which are going to be able to map to these blocks over here. All right. But it's only but let's say that it's a program that even takes a little bit more than that. Then essentially what is going to happen is that a number of blocks tends to need to be swapped in and swapped out for another slot, essentially, constantly driving the amount of cache misses that you're actually going to have. Does this make sense?
It does. So it's a balance between the number of blocks and slots and what and frequency of use in the file of the program as well.
Yes.
Okay.
So it's not
Adapt.
always that straightforward, to another way that you can sort of like have sort of like the best of both worlds, all right, would be to use this other method that we're going to be talking about now, all right, which is the set associative mapping. All
Okay.
right. So the set associative mapping, all right, divides our main memory into blocks, as we already discussed. It also divides our cache memory into slots, and then it groups, all right, our slots into sets. All right. So essentially, each set will have a number of slots, and then each set, all right, will be able to refer, all right, to a subset of blocks in memory. All right. So essentially, that would mean that you would have a number of slots which will be able to map, all right, to the same subset of blocks. All right. That is essentially the way that you get sort of like the best of both worlds. All right. So the way that you would map this is that you would need to first and foremost determine the size of your sets. All right. So in this case, we are setting our cache to have sets of 2. All right. So every set has 2 slots within it. All right. Which basically means if we have 2 to the power of 14 slots, all right, then it means we have 2 to the power of 13 sets. All right. And those sets will then be able to map to your blocks accordingly. All right. So essentially, the way that you would split up the address would be that you would have 13 bits used in order to identify the set. All right. 14 bits in order to be able to identify which block from that set, from that subset over here of blocks that you're actually going to be mapping to. And then again, you'd have the 5-word bit in order to identify which byte you're actually going to be referring to. This essentially is the best of both worlds between the fully associative mapping and the direct mapping that we've seen before. All right. The fact is that you would have to do less swaps, all right, in cache in order to increase your hit ratios. In fact, the whole point behind cache memory is in order to increase cache hits and reduce cache misses. And it's not outside of the realm of possibility in order to see cache hit ratios larger than 90%, as I mentioned previously. All right. Now, what really happens whenever you are performing one of the memory read cycles or the memory write cycles is that what you do is you first place the memory location that you would like to read within main memory. All right. And if that main memory happens to be within cache, it will be cache hit, and the controller will literally pass the data that is within the cache to the CPU. However, if it is a cache miss, meaning that it doesn't exist within cache, then what it would do is it would retrieve that memory location. All right. It will store it in a free slot if there happens to be a free slot. All right. If not, then probably it needs to follow some form of replacement policy to see which slot it's going to replace. So essentially, you swap in and you swap out a block into a slot. Okay. Now, obviously, the replacement policy would be determined by replacement algorithms, and there are different forms of replacement algorithms that you might want to use. You might want to use, for example, the least recently used. All right. Essentially, you would discard the item that you haven't really used as frequently. This is an ideology saying that if you haven't been using this this slot recently, then essentially the probability is that you're not going to be using it anymore. All right. Or else you might use what is known as a first in, first out architecture. So the first one that came in and has been here for quite some time, you would replace it with a new block within that slot. Again, you would need to keep track of which blocks have been written into which slot first. All right, and then you would replace them accordingly. Another one would be the least frequently used. All right, so this would count how often an item is actually needed. All right, and those which are needed less are then discarded. You could also use the opposite ideology, the most recently used. So the item that you have used most recently might be something that you're not going to be referencing again in the very near future. So in that case, you would replace it with something else. Could also use a different ideology, such as the adaptive replacement search. Essentially, you would have sort of like a combination, maybe, of the least recently used or the least frequently used, in order to again try to improve results. Or else you can literally go for a random replacement policy. All right, where you would randomly select a cache slot to discard its data and load in this new data, essentially. Okay. But whatever the replacement policy is, it also the performance of it is also going to be determined by the type of cache memory that we actually have. All right. In fact, there are two different types of cache memory. There's what is known as write to through cache, and there's also what is known as write back cache. Write through cache, essentially, whenever you're going to modify the data in cache, it will try to simultaneously write the data, all right, in cache as well as in main memory. All right, in order to make sure that the data stored in cache and in main memory are exactly the same. All right, however, this is slower. All right, the reason is that obviously if you're going to write in cache and in main memory simultaneously, then you will need to make sure that you're actually communicating with main memory. which obviously would slow down the system. All right. However, you could use a different system, all right, which is the write back cache, which makes use of that dirty bit that we were talking about earlier, all right, which would write data to the cache originally, and then when it is swapped out, all right, when that block from that slot is swapped out with a different block, then the data is then written back to that main memory location, therefore updating it later on. All right. So essentially, your cache read and write policies would work in this way. So essentially, if you're reading, all right, you would check to see whether the data is in your cache. If yes, you would forward it to the CPU. If no, you might either load through the CPU through main memory, which basically means that you are going to forward, all right, the word that you need, all right, as cache slot is actually being filled, or you would first fill the cache slot and then forward the word into main memory. So this would actually be loading into cache as well as loading to the CPU simultaneously. All right. Whereas with writing, all right, you would first get the request. You would check to see whether the data is in cache. If you're writing through, you're writing to both the data both to the cache as well as main memory, or else you're using the write back. All right, which basically means that you are going to write it at a later stage when that block is flushed out. Otherwise, if the data is not within memory, you can use either bringing the block into memory and then loading and then updating it, or else you would just directly write it to main memory in that case. All right. Again, these read and write policies would depend entirely on how your CPU is structured, essentially. All right. In some CPUs, you might also have caches which are used in order to separate both data as well as instructions. So you would have one cache storing just data and another cache storing instructions. The reason is that when you are storing instructions in one cache, you're actually not writing anything, you're just reading. All right. And you're only writing data, so you might be able to eke out yet more performance and more cache hit ratios by having this this distinction between instructions and data. All right. Obviously, that means that your program was actually run faster because retrieving instructions would actually be a lot faster. All right. Another thing that you also need to take into consideration is that since our CPUs are actually making use of multiple cores, it is not outside of the realm of possibility to have what is known as multiple levels of cache memory. Essentially, what would happen is that each core, all right, would have its own cache associated with it, therefore increasing the performance of each CPU individually. However, we also know that each core might possibly need to communicate, all right, with other cores, or each core might need to communicate with similar blocks of memory. So what could happen is that you would have different levels of cache, all right, which sort of like act as buffers between these caches. So you would have the level 1 cache, which would be associated with each core, which would obviously be quite small, but they would be very fast and they would be very direct with each core. Then you would have a level 2 cache, which in turn would be able to store more data. However, it would be able to service more cores simultaneously. And this principle can keep on going all the way down until main memory. So you might have multiple levels of cache, all right, with obviously various degrees of speed as well as capacity. Notice that the closer you get to your CPU, the greater the speed, however, the smaller the capacity, like with everything else. All right. Conversely, the further away you get from the core directly, all right, the slower it becomes, but the greater the capacity. All right. So essentially, you might have a cache miss in level 1, in which case you would check your cache at level 2. All right. If you have a cache miss in level 2, then you check your level 3, and so on and so forth. All right, depending on obviously the number of different levels of cache that you might have within your system. All right. This would obviously make it much better, all right, especially when you're running multi-core CPU configurations, which are very, very, very much the order of the day when comparing when comparing um, uh, the typical um, uh, the typical CPUs that we run nowadays. All right. But essentially, the whole concept behind cache can be generalized down again through the idea of storage hierarchy, since cache memory sits in between the CPU and main memory, tends to be a lot faster than main memory, thus allowing us to be able to communicate with the CPU a lot faster. But obviously, it has a much smaller capacity than obviously your main memory. Any questions, guys?
Not from my end. Thank you.
All right. So I'm going to stop here for today. What I would like you guys to do, all right, as a little bit of homework, and even in order to preempt our last lesson that we're going to have for this subject, all right, I would like you to read, all right, the slides, at least for this section for the data storage, in a little bit more detail on your own, so that we'll be able to go over the elements that we might have not covered in the first term for the principles of computer architecture. Okay, so that we will be able to focus on the new stuff. As you can see over here, we're going to be talking more about magnetic storage, like hard disks, and what they are like, and how they work. There are a number of different elements that we've already sort of like discussed in our first in the first term. All right, so please take a little of a look through them. All right, obviously we'll then talk about the other stuff that we haven't really covered up to this point, so that we'll have a little bit of a faster go at these slides. Okay, and then we'll be able to talk about these as well as operating systems, all right, in our next lesson. Okay, it might be the case that in our next lesson we will need to do a little bit more, all right, in order to be able to make sure that we have covered everything that you would need for the exam. All right, is that okay with you guys?
Yeah, that's more than fine from me.
All right. Okay. So thank you very much for listening. Have a good evening, and I will see you guys in our next lesson. Okay.
Thank you, sir. Have a nice
Thank you
evening.
very much.
Good
very
evening.
much. Ciao,
Thank
ciao.
you, sir.
Bye bye.
Sir, bye.